In this lesson, we're going to take a look at elastic and inelastic collisions. Now, from the reading, you know elastic collisions have kinetic energy conserved, and in inelastic collisions, kinetic energy is lost. And if you think about an inelastic collision, what happens with that is you have two things that hit each other, and so initially they have their undamaged shape. But afterwards, this thing's moving this way, this thing's moving this way. They collide with each other, and because of that, they wrinkle up a little bit, they collide a little bit, the bumpers crush a little bit, and that takes energy. It causes these things to deform, it causes them to heat up, gives off big sound waves, so all the kinetic energy that we had before, we're not going to have afterwards. Even if they do bounce apart a little bit, that deformation took some of their kinetic energy and changed its form. So it's no longer got the same amount of kinetic energy it started with. But there are elastic collisions where the kinetic energy is not lost. And usually, I think of elastic collisions, I think of like two billiard balls or pool balls. When they smash into each other, that's almost perfectly elastic because those things don't deform. They smack into each other, they bounce apart, and so the kinetic energy stays essentially the same. And so when we have an elastic collision, the kinetic energy before the collision is equal to the kinetic energy after the collision. And remember, kinetic energy is equal to half mass times velocity squared. So when we have two objects, we're going to use V1 and V2, and when we have before and after, we're going to use V1 prime, V2 prime. So really, when we say an elastic collision, we mean the kinetic energy is conserved. Elastic KE conserved. And so there's an equation for that, and that equation is simply 1/2 mass times V1 prime squared plus 1/2 mass 2 times V2 prime squared equals 1/2 M1 times V1 squared plus 1/2 M2 times V2 squared. Now, V1 prime refers to the velocity before the collision, V2 prime refers to velocity before the collision, V1 refers to velocity after the collision, and V2 refers to velocity after the collision. Okay? So that's what it means when we say kinetic energy is conserved. The total kinetic energy of everything before they collide is equal to the total kinetic energy of everything after they collide. Happily, this can be condensed into a much simpler formula together with the law of conservation of momentum. Remember, this is kinetic energy conserved. When momentum is conserved, that's M1 V1 prime plus M2 V2 prime equals M1 V1 plus M2 V2. So these are both true in elastic collisions. This is true for any collision. If we take this law and combine it with this law, we can get, through a whole bunch of algebra that I don't have to go through, that V1 prime minus V2 prime is equal to the opposite of V1 minus V2. This equation is really, really handy because it doesn't involve the masses and it doesn't involve any of the squares like was going on in this kinetic energy equation. So this works only in elastic collisions and only when they're in one dimension or they're head on. But that's all we're going to deal with. We're not going to have things move off at angles. So with this equation and the momentum equation, we can solve a question like this. Say I've got this 2 kilogram cart that's moving this way at 4 meters per second, and it hits this other cart that is 3 kilograms, and it is at rest. And afterwards, I want to know the velocity of both carts. I want to know the velocity of the 2 kilogram cart, V1, and I want to know the velocity of the 3 kilogram cart, V2. Right? So if I was listing my known information, I have V1 prime equals 4 meters per second, M1 equals 2, M2 equals 3, these are both in kilograms, V2 prime is 0, and I want V1 and I want V2, and this is perfectly elastic, and that tells me kinetic energy that I start with equals kinetic energy that I end with, and it's a collision, so that tells me momentum that I start with equals momentum that I end with. Okay, so that's everything I know. Now I'm just going to go ahead and start plugging it into my equation. So momentum is equal to 2 times 4 plus 3 times 0, and afterwards it still has to be the same, so 2 times V1 plus 3 times V2, right? So this gets me 8 plus 0 equals 2V1 plus 3V2. Now that presents a problem we've not had to deal with before, and that's where we have two unknowns in one equation. But when we have that, all that means is we have to go and grab the other equation that will allow us to solve for that, right? So I have this other equation that says V1 minus V2 equals the opposite, or negative, and these are primes, of V1 minus V2 afterwards. So V1 prime was 4 minus 0 equals the negative of V1 minus V2. Well, when I distribute that negative through there, I get 4 equals negative V1 plus V2, right? Negative times positive is negative, negative times negative is positive. And now I can add this V1 to both sides and get 4 plus V1 equals V2. And that lets me make that substitution right here for V2. So I can say 8 equals 2 times V1 plus 3 times, instead of V2, I'm going to write 4 plus V1. Now, simplify that a little bit, and I get 8 equals 2V1, 3 times 4 is 12, 3 times V1 is 3V1. Now, if I subtract over this 12 to combine like terms, I get negative 4 equals 2 plus 3 is 5V1. Right? And divide by 5, V1 equals negative 0.8 meters per second. That tells me this cart is moving this way at 0.8 meters per second. And I can also find V2 because I have this equation that I put that box around earlier, which says 4 plus V1 equals V2. Well, now I know V1 is this negative 0.8. So I take 4 plus negative 0.8 equals V2, and so that's 3.2 equals V2. So this cart is moving this way at 3.2 meters per second. So it is a long process, but nothing is too hard as long as you are paying attention to what information you're given and how it works in each one of these collisions. Now, if you're just supposed to check to see if something is elastic, you can see if the kinetic energy before and after is the same. If it is, it's elastic. If it's not, it's inelastic.